Welcome back and welcome to my channel, and this is Dora. In the previous video I show you how to create the geometry of an offshore wind turbine platform, and in this tutorial I will show you how to create the computational mesh to be used in OpenFOAM. So this is the geometry we created using Salome, and we exported to STL format, and this is the final product, which is our mesh to be used for the OpenFOAM simulation. And but before continuing, I need to confirm that this mesh is still very coarse and it might not be suitable for serious validation and verification processes. But for learning how to create the mesh and how to simulate and floating semi-submersible offshore wind turbine platform, this is a good tutorial, I think. Okay, so before going ahead, we have a problem, and here you can see here when I created the geometry, I created a triangle, and it's like in X direction, it's like 30 degrees different from our flow. I want to be make it like this instead of our STL file. So we need to rotate this STL to our desired direction. So I will do it, and I need to start. You can do it in several ways, and you can even do it in Salome, or you can do like in external softwares like Blender or something like that. And but I will use OpenFOAM to rotate, manipulate this STL. So let's go ahead and do it. So this STL, this is the initial one, and should be translated like rotated like 30 degrees in counterclockwise Z direction. This is before and this is after. So I'll show you how to do it. And to make it, we need to use surface, the command surface transform points. Okay, I forgot which OpenFOAM version is this, so I will make it sure. Okay, so this is OpenFOAM V2206, so I will use it. So minus. So if you don't know what to do, you can just type help command and dash help, and it will show like the general guideline for this. So I will do this minus rotate. You can do like roll, pitch, yaw, or something like this, and rotate that. Negative 30 degrees, minus 30 degrees, and I think roll pitch shall work better. Yeah, roll pitch. Okay, and the angles should be inside the double quotes or single quotes, 0 0 and negative 30 degrees, and our file name is float.sdl. To output file name is float3.sdl. Let's see. Okay, so I okay, transform, and oops, I think it's positive 30 degrees, so I will do it positive 30 degrees and read again. Okay, here we go. Now we have the SDL file rotated to our desired direction, and so I will, okay, I only use this one. And another thing we need is the background blockMesh to generate the SnappyHexMesh. So I will need to define the dimensions of this background domain, and I will use this rotated STL file as a reference. And we can see here the x is from negative 26 to positive 40, and the y is negative 37 to positive 37, and z is from negative 6 to 26. So I will make a box larger than this geometry STL file, and in the para view you can do it in sources, search, and box. Okay. So this is for reference, and the box center is 0 0 0, and x length is like 300, and y length is, okay, I'll give it 100. Okay, I make it 400, 100, and 100. And I will use the wireframe so I can see the domain size. It's a bit tight, so its x is not so bad. The y is a bit tight in this direction, and z is okay. So you can see here from x range, y range, and z range. So I will increase the y range by like y length to be 150. Okay, this is a bit better. Okay, what looks like my, oh, I made z quite high. Okay, so this is like the result. So you can change the z direction, like, okay, I also did 150. Yeah, this seems okay. And yeah, this is my, I think this is my main mesh size. Okay, now we have the dimensions of our block mesh. So all we need is to go to the system blockMeshDict and edit these vertices, these dimensions to these values. So x range is from negative 200 to 200. So these are x, y, and z directions. Okay, and y range is negative 80 to 80. So sorry, this is my main mesh, so I will use this box. So you can do it like from negative 75 to 75, and from negative 75 to 75 for Z. But I did 160, and it's negative from negative 80 to 80 for Y and Z directions. And you need to define the number of cells in each direction. In X direction, I give 50, and Y and Z to be 20. So the mesh will be a bit coarse. Of course, I will create the original. You don't need this step because I want to just save my computations. And okay, copying them shall take a lot of time, so I think I will make a new case. Okay, cool. So this is not org, this is I will write v1, and I will work everything in there. So I will move to C v1, will walk from there. So to create the mesh, I will first clean up the case from tutorials. I will write block mesh, and to visualize paraform -touch. If you are on Linux and like Ubuntu, you don't need this touch, because I want to see the result in my para view of Windows. So I'll go to my v1, and okay, now you can see the mesh. And sorry, I need to copy the float 3 too. So this is float 3, and I need to confirm the name. This sets the solid float. So this name is the name of our patch, which will be used by SnappyHexMesh. So I will need to confirm whether it's alright or not. Okay, here is float, and so it starts with solid and ends with n solid, and the names should be the same, so it's okay. And I will check whether everything is alright, and for my OpenFOAM or blockMesh, I will use the wireframe, and this is the initial situation. Okay, so I need to move this STL file to constant and try surface here, and I already moved, so and I need to rename it as a float. Okay, so for full demonstration, I will do the renaming too. Okay, now I have the file called float, and it will be used by SnappyHexMesh and also SurfaceFeatureExtract. First, I will talk about the SurfaceFeatureExtract, because this geometry has several sharp edges which need to be refined properly. Otherwise, these edges will be very coarse, and these will be very rough. So we need to be careful about this, and all we need to do is to run the SurfaceFeatureExtract. This is I use the OpenFOAM ESI version, which is 4 digits, like 1912, 1906, or 2006, and now this is like almost the latest one, 2206. It means it was released in the June of 2022, and now we have like 22 12, which was released in 2022 December. Okay, but anyway, all of these are very similar, and for this purpose you can use any OpenFOAM in this series. I don't use OpenFOAM foundation version so much. But anyway, these are very similar. Okay, and the main reason for not using is the overset mesh in ESI version, which I want to use, and in the foundation versions there is no overset features yet. Okay, let's go back to our work, and I will create the surface features for this STL file. I mean, as float.stl. I will make it consistent in this tri-surface. Okay, this guy. Okay, and to make it I need to tell the name of the STL file, which is float.stl, and this include angle is the most important parameter, and I will give it 150. It means if it's 0, it will select no edges, and it's 180, it will select all the edges. So 150 is like a sweet spot, and most of the time it will work. And yeah, you can just disable the non-manifold edges or not, but I will do it and have a look. Okay, so the next step is surface feature extract, and so OpenFOAM will read this STL file and detect the surface features and write the outputs. It means the object files as the output for viewing. So let's look at these outputs, and these output files will be located in constant and extended feature edge. And there we have a lot of objects, and I don't know which one I should open, but yeah, this one is okay. Generally, we can open up all the files. Okay, and we can see it detects almost like all the edges which are important. Okay, now this step is okay. Okay, so I will delete them from view, and the last step is to use the SnappyHexMesh, and this is my SnappyHexMesh dictionary for the beginners. It's located in the system directory of your case directory, and this guy is the SnappyHexMesh. Okay, and if you open up, and you can see the SnappyHexMesh, and the first 2-3 things are the most important things. I mean, everything is important in this file, especially the top parts, and these are the most. And the castellated mesh, snap, and add layers. In this tutorial, I will disable the add layers to because this flow around this offshore wind turbines is mostly due to the waves, and the viscous effects are like smaller. And I actually, if you are very serious about these viscous effects, you should try to add a lot of layers, and you should be careful about the Reynolds numbers. But in this tutorial, I assume these effects are small. All we care about is uh, the response by the wave load. So I will disable the boundary layer mesh, and in the geometry we need to tell the file name, which is located in the constant and try surface, as I mentioned before. Okay, and I want to add a refinement box from 5 to 20 in the Z direction, and it's for the uh, free surface. Actually, you can use topo set and refine only around the free surface and only around your structure, like in TTC HAL tutorials of OpenFOAM. But this method has some problems, especially if your geometry is a bit complicated. Sometimes the SnappyHexMesh just cannot generate a good mesh. So I will stop using that approach, and I will use refinement box around here to refine the free surface. Okay, so we have the gaslighted controls. I will not cover the details, and these are the features. I want to tell SnappyHexMesh that we need to be careful about these edges. So what are these? These are the edges we generated from our uh, SurfaceFeatureExtract command previously, like here, and this file is stored here in the constant and try surface directory by our SurfaceFeatureExtract utility, and the level is 0. So it says I will not force SnappyHexMesh to refine the edges very finely. It means these edges should be care, but not ultra refined. If we increase this level, the refinement around these edges will be very high. So to cut to the chase, if we put the setting like this, the open SnappyHexMesh will take care of the edges, and it will not refine too much. Okay, and here we have refinement surfaces. So we tell SnappyHexMesh to refine from level 2 to 4. So what does it mean? So level 1 means, level 0 means it will not refine, and it will only use these background block mesh to create the surface mesh. And level 1 means it will divide each cell divide each cell once, and level 2 means each cell twice. So 4 means we have 4 times of refinement. Okay, so the surface shall be refined from 2 to 4 times. Okay. If we can just force like 4 to 4, but it will make the the surface mesh uniform, but it will be computationally expensive. So I will use it only 2 to 4. Okay, and resolve feature angle 60. So this is like the sweet spot, and I will not cover for now. And for the refinement box for our free surface, I will keep 2 to 2. Okay, so the free surface should be very consistent, so the refinement is also kept consistent. Okay, another thing we need to be careful is the location in mesh. So it means any arbitrary point inside our fluid domain should be used. So we need to make it we have good values, correct value. So I will create a sphere. So in the source search of in ParaView, you type sphere, okay, and the center is 0, 0, 0, and radius is 0.5, and I will look at it. Okay, where is our here? I will make it bigger. Okay, radius is like 2. Okay, this is bigger. So it means if I set the location in mesh to be 0, 0, 0, the mesh will be inside this geometry. So it will tell the SnappyHexMesh that we only want this part. We don't want the outside of the geometry. Okay, so but we want the mesh outside the geometry. This is the whole domain, and we make it empty inside our geometry. So all we need to do is to keep the location inside our desired place. So we have 3 choices. If the location in mesh is outside the background boundary layer, block mesh, it will not mesh. So the SnappyHexMesh will not generate any mesh. And if it is inside the SDL file or geometry, the SnappyHexMesh will only generate the mesh, volume mesh for this geometry. And if we put the location inside in mesh to somewhere inside our fluid domain, it will generate our desired fluid domains outside of the geometry. So I will set like -10. Yeah, so here it's -10 and +10. Okay, I will make it to okay. So our domain location in mesh is here. It means we will get the fluid domain or like this. Okay, anyway, it's a very important factor, and you should be careful. And the rest is not that important, and I already skipped the layer addition, and the rest are like mesh quality controls and the number of the smoothing iterations. So generally the default values are good, just okay, and if these are not good, we will think about the other ways. Okay. So I will generate the SnappyHexMesh. Right, it means it will only generate keep the last generated mesh. We have 3 steps: castellated, snap, and add layers. And for each step, SnappyHexMesh generates and writes a mesh. But if we use overwrite, it will only generate the last step. So it's after the snap. Okay, so let's see the mesh. Maybe it will take some time. Okay, it's taking a bit time, and I want to make it parallel. So before doing going parallel, we need to confirm that there is no 0 directory in our case directory. if there is some zeros, we will change to 0.awk, because there may be some complications or errors if our boundary conditions are not right or something, but we will not care about these. Okay, so in the system decompose predict, we can set the number of subdomains to be used parallelly, and I will use Scotch. This is this method relies on OpenFOAM to decide how to divide the domain to these numbers, and we can have different other methods, but I will use this. So the command is decompose bar and negative minus force. It means it will force OpenFOAM to delete if there are any these processor directories. So I will, and now these are okay, and I'll use SnappyHexMesh in parallel. So mpi run minus mp6. So this is the number of my processors, and the command is SnappyHexMesh minus parallel minus overwrite. It should run. Okay, it's running much faster than before. Okay, now we finished meshing, and we want to check whether everything is all right. So I will run the check mesh in parallel. mpi run minus np6 check mesh minus. Okay, I will make it a bit longer so it's easier to read. Parallel. If you use mpi run, and if you want to run parallel, you always need this parallel command, and constant is for to tell OpenFOAM that we only care about the last mesh we generated, and it will be stored in our constant directory. And the check mesh is okay, and we have our float object and in the patches, and we have 520,000 cells, so it's a little bit high, but especially for a tutorial, but I will, it's okay. And okay, I will make it reopen it. Okay, and here, and use OpenFOAM reader, and here we just uncheck the skip 0 time, and we choose the case type as decompose case, because our mesh is already decomposed mesh. So apply, and I want to see this, everything is all right. Seems okay from the outside. And now we have our geometry, and I will check. Okay, I'll create a slice and check the inner parts, and you can just click on this main OpenFOAM, and you can add the different patches here in the mesh regions. I want to add my float. Okay, click float and apply, and to see it, I need to use an extract block. So in the source and search, I search all the time. Okay, extract blocked, because it's open for ParaView has a lot of different utilities sources. Okay, now this is my mesh, and I want to see it in surface edges. So you can see some are do refine twice, and some are thrice, and some are fourth. So we have different refinements, and our mesh is generally okay. That's all for this video, and in the next video I will show you how to set up the boundary conditions and overall physical properties as and numerical schemes, etc., especially for a 3D simulation. So if you are interested in, if you want to learn such tutorials, please stay in tune. Thank you very much.